Welcome. This is the last class of this diffusions, effectively the last class of this diffusion series. To close today, we have one of our colleagues, Dr. Dheeraj Nagaraj. Dheeraj is a long-term friend and collaborator. He's in DeepMind. He received his bachelor's and master's from IIT Madras and his PhD from MIT. And he's a research scientist in DeepMind. Is going to talk about some of the work they have been doing there. Dheeraj, take it away.
Yeah, sure. Thanks a lot, Sanjay. Super excited to talk about our recent work on using diffusion models for constraint generation with both discrete and continuous elements. So hopefully you've followed the course so far, which has been super exciting for me. I've seen the lectures on YouTube. You learned about continuous diffusion, how it can nicely generate images. You've learned about discrete diffusion, which can generate language, and so on. Now I'll introduce you a framework where you can generate both continuous and discrete mixed mode generation. And this is our recent work, which is under submission. This is from early this year. Okay, this is with my co-workers, co-authors, Karthikeyan Shanmugam, Gautam Govindanil, and Sachin Yadav. Okay, so we have generative modeling where we have a data set D of n samples, right? And of course, the primary motivation here is, okay, we want to generate more samples from the same distribution. We are interested in the individual samples themselves rather than statistics of these samples, as in classical MCMC. So when we generate an image, we want to look at that image. We don't care about the pixel density statistics or something like in Markov chain Monte Carlo, right? So the most successful approach here, which everybody is talking about for the last 3, 4, 5 years, is autoregressive model, which generates text word by word, almost, or token by token, by learning to generate text from a large corpus, right? And the other successful paradigm here, which is the object of study in this course, is diffusion models, where you generate images by denoising white noise, which is Gaussian white noise, right? You just get you have something which has no information about anything, and then suddenly you denoise it to get images, for example. Okay. Okay, so taking a step back, this is not just about text or image. We have so many distributions we care about, right? Which I'll discuss. And this talk will not be about either text or about images. It will be something else entirely. It won't involve either of these modalities. And real world data could have discrete elements and continuous elements, and it could be mixed mode. That is, some of them could be categorical, some of the elements could be continuous, right? Some of them could be bounded in certain ways, constrained in certain ways, right? And we're interested in modeling those accurately, right? So when you see text, right? So in autoregressive model, the text is not supposed to be representative of the samples it sees in the internet, because that might be very offensive. What autoregressive models are finally do is they want to please the user. Similarly, what the images that diffusion models output in is not necessarily what natural images look like. They're what are supposed to be pleasing to the eye of the humans. But what we care about now is to actually capture the underlying distribution accurately, as is important in the sciences, for example. Okay. So, okay, so before we delve into that, let's understand generation with explicit constraints, right? So this is the classical case. There's a constraint set specified explicitly. You design algorithms to generate random variables constrained to the set. For example, we might want to sample from a convex body to compute its volume and so on. It's a classical problem in TCS, theoretical computer science. And you design the algorithms knowing that you have this specific convex body and you want to sample uniformly from within it, right? Or you can have something in the discrete case. You can have something like the Sudoku, right? You have things which are filled in, and you want to fill in the blanks. And let's say you want to solve this, you just hard code that these are the constraints. Don't change these, change the other things, so that the constraints are satisfied. Okay, so these are the two examples with which I can give you for explicit generation with explicit constraints. Okay, let's think about implicit constraints or unspecified constraints, like what we are dealing with now. Okay, we have a lot of data available. We see data everywhere, and everything can be used as self-supervised learning, like we do in autoregressive models or diffusion models, and we know it is constrained, right? And we don't know how to describe these constraints explicitly, and it might be impossible or maybe implausible to do so algorithmically, right? So when you see a corpus of text, it's hard to describe what makes text grammatically correct or look good. It's kind of something you know when you read something good, but it's hard to actually describe it algorithmically, right? Or what makes a picture appealing is a constraint. But we don't care about those constraints in this. We care about something more scientific, let's say. Okay, so first example which I want to introduce is for implicit or unspecified constraints is molecule generation, right? So suppose I have a data set with say 100k molecule structures. Okay, scientists have figured out that these are the molecule structures using like X-ray, crystallography, and so on. There are molecular dynamic simulations and so on, and they tell me that okay, there are these 100k molecules. These are the coordinates of each of their atoms, and these are the different atom types. Okay, so and then these are all valid molecules. So then the question is, what is a valid molecule? And it turns out it's a very surprisingly hard question to answer. One rule of thumb, which is that valencies are satisfied, bond angles and bond lengths are plausible. But there are some molecules where these kind of simple bounds are not do not hold, and they're more exotic. And there are about some percentage of this data set will contain things like that. So the question is, okay, we have this heuristics as to what are these implicit constraint, what makes it a valid molecule. Are these things sufficient or are these necessary? It's actually hard to tell. Okay, so okay, this is in the case of like say simple organic molecule, like say there are a couple of benzene rings and they're connected to each other and so on. Tens of atoms in this molecule. What about the harder question? So there are proteins which have potentially thousands of atoms, and we want to design a protein which bind to a specific kind of substrate, right? And how do we describe this mathematically? It is actually a very hard to describe what makes a protein bind to a specific kind of a substrate, right? So it's a constraint, and we know that it is a constraint. We know that if we have data on these protein structures, we know that they bind, and it is an implicit constraint satisfied by our data set, but we have no idea what makes it actually bind, right? It is hard to make an algorithm think that way, right? So I hopefully have given you some clues about what we call implicit constraints in this case. A second kind of example is layout generation, right? So you have this layout. I'm guessing many of your graduate students, and you have to type away in LaTeX. You'd have something figure like this, and then text, and then there's a title, and there's another table, and you need to make all of this look good. Okay, okay. So there's a constraint, of course. These should not overlap, and uh, what makes it appealing? It's hard to say what makes it appealing, right? You can see that something appeals to you when you see it, but yeah, that's a soft constraint which I don't know how to describe exactly. Right. So, right. So before we solve these problems, so let's think about how to actually think about constraint and in terms of generative modeling. So the most dominant paradigm of generative modeling, let's say, is autoregressive models. Okay. So how do they behave? Okay. So we generate joint distributions coordinate by coordinate or token by token with a neural network. So here is an animation. There's a neural network. Initially, there is no input. It generates the first thing, let's say G. Okay, and then it says that okay, the first letter is G. I'll give that as the input, and then it outputs E. Okay, and then I'll say first two letters are GE. What could be the next one? And then it's a N, and then N is goes in, E goes in, R goes in, A, P, E. So this is how you would generate in an autoregressive model. This is how Gemini works. This is how ChatGPT works, hopefully. And right. So this is how a lot of generative modeling is done. Right? So let's say you have Sudoku. Of course, when it comes to language, we are all used to writing left to right, one word by word. So this seems like an intuitive way of generating language. Now let's look at how an autoregressive model could solve a Sudoku on the left corner I have the actual solved one, and the right is unsolved one. So let's see. So it would go 4, 3, 5, 9, 8, 2, 5, 1, so on. So when you are solving Sudoku, is this how you would naturally think about it? Okay, or is this even a best way to solve it? Right? Because there could be some things which are obvious, as in there could be only one thing which fits in somewhere, and some things could be ambiguous, as in many things could be plausible in that position, and you can't figure that out unless you fill in the other blank spots. Right? So it seems like intuitively autoregression is not the right method to solve sudokus or problems like where there are constraints which are not necessarily look like constraints in text, for example. So should we move beyond autoregression to solve such problems? So that is a question we ask. Okay. So, okay, so we turn to the other dominant paradigm, okay, because we believe that autoregression cannot solve such problems, or can find these problems hard. So maybe move to diffusion models. Of course, you've spent the semester, I guess, studying continuous diffusion models. So let me still give you a quick primer. So you have a picture of a bicycle from CFAR data set here. You kind of add Gaussian noise to it until you see only white noise. Okay, this is the destructive Ornstein-Uhlenbeck process. dxt is equal to minus xt dt plus root 2 tbt. And then there's a constructive process you learn through score matching, right? And you get this dxt is equal to plus xt dt plus this term grad log score function, grad log pt, which contains the information about your ground truth distribution plus, Brownian motion. Okay, and then what do? We learn the score function grad log pt via Tweedy's formula, and we just sample new images from pure noise. Okay, so let's think more about this in comparison to autoregressive models. So here all pixels are generated simultaneously, instead of pixel by pixel. They're not generated one by one, such as in autoregressive models, right? And this can be, of course, sped up by coarsening numerical discretization parameter, and sampling steps can be varied between, say, 1000 to 25. This is not a feature in autoregressive models unless you design something much more complicated than the standard autoregressive models. You can only generate one token at a time. But here there is a continuous time which can be tweaked with to speed it up, right? And this becomes a feature of diffusion models. Okay. So, okay, so what about discrete and mixed mode diffusion models? Real world can be discrete or mixed mode, such as layouts and images plus text, images embedded in text, and so on, right? Um, and one of the questions we ask is, can we write down diffusion models for discrete data and discrete continuous data? And why would this be interesting? See, this is interesting because we can generate layouts like this. So this is our layout generation kind of experiment, where there is a type of box, that is, it could be text, it could be image, it could be table, and so on. And there is a position of the box, right? And this algorithm tries to figure out both position and the type of box simultaneously, right? And that's why discrete continuous modeling can be very helpful, because you might want to tell it what type of box it is to figure out where it should go. And depending on where it is and what size it is, you might want to figure out what type of box it is, right? So there's some information transfer in that case. Okay. So I guess last couple of lectures you've studied discrete diffusion with masks. You have a continuous noising process, you got the continuous diffusion models. If you have a discrete noising process, you get discrete diffusion models. Okay, this is not called diffusion in any other literature, but in machine learning, it's by analogy to continuous diffusion models. These are called discrete diffusion models. Well, let's stick with the new nomenclature, I guess. So the first work was D3PM by Austin et al., and there are lots of variants and lots of follow-up work, including our group, and Sanjay has done a lot of work on this, and everybody's working on this, and this is a new hot idea in Silicon Valley, the thing which is supposed to replace autoregressive LLMs. Okay, so how do we do mass diffusion? So okay, so you need a noising process. So suppose we have a word like this. Okay, at step one, you flip some to mask with probability p. That is, you just go and block it, and in step 2 you block more, and so on until you only have masks. Okay, so now you've completely destroyed information. Okay, and then what you do, you start with full noise and you predict original and apply Bayes rule, and then you predict original, apply Bayes rule, and so on until you generate whatever, a word which makes sense. Okay. uh, to compare the pattern of generation, in the LHS you have mass diffusion model, on the RHS you have autoregressive models. It generates one by one. You have this nice uh, lower triangular structure there when you look at it, how it's generated across time, but there is no such structure when you look at mass diffusion models. Okay. There's another class of models called multinomial diffusion, which contains multinomial noise. I mean, academic papers these days, it's not very popular in the academic paper literature, but I assure you this is actually quite good. Multinomial diffusion. Okay. So okay, so you have something like this. The gray spaces here are not real. It's for illustration purposes only. So you flip independently sampled positions with probability p to something independently sampled. So we go and insert gibberish, k and h, which don't belong in that place, right? Until everything is gibberish and it doesn't make any sense, right? And then you start with something full noise, which doesn't make any sense, and slowly keep on flipping it until you end up with uh, something which makes sense. Okay, there's a typo here. Unfortunately, I'll correct it in the next iteration. But okay, the point is, what does multinomial diffusion allow you to do? It allows backtracking, right? You can do multiple flips of the same token. It does backtracking, and that is, it can have rough drafts, and it can keep refining it by correcting mistakes. It's a feature. It's a fundamental feature to this, and it is not a fundamental feature of mass diffusion model unless you go and algorithmically endow it with that additionally. Okay, so okay, that's not a typo. I just messed up the animation, I guess. So, and then you finally generate the word. Okay, so to give you a comparison to of some key points, let's compare autoregressive diffusion, mass diffusion, and multinomial diffusion. The generation order in autoregressive models is causal, left to right. Mass diffusion is arbitrary; it can generate in any order, and multinomial is also arbitrary. In autoregressive models, noise versus signal is known as and it's not even a question. In mass diffusion, it is known. If it is masked, then it's noisy. If it is not, if it's some token, valid token, then it's a signal. Similarly, in multinomial diffusion, unlike these two situations, you don't know if you see um, a token in a position, you don't know if it's real token or or did it come there because of noise. Okay, so the real place where diffusion models shine is when tokens per call. Autoregressive models can only generate one token per call, whereas masked and multinomial diffusions can generate multiple at a time, right? The advantage of mass diffusion is it can backtrack, it can give a wrong answer and then go and correct it after it realizes it's wrong, but autoregressive and mass diffusion cannot do it. And diffusion models can also do in painting, right? Autoregression can only add things at the end, but diffusion models can see, say, you have paragraphs 1 and 3 and you ask it to fill in paragraph 2, they're able to do it. Right? So these are some of the advantages of diffusion models. Okay. Okay, so how to learn discrete diffusion? Most proposals for learning hinge on predicting a noise sequence. So I guess you've studied this in the last couple of lectures on discrete diffusion models. So let me skip this part. Okay. Okay, so what are these kind of diffusion models good for? Potential, right? So they can be useful for planning tasks, right? What do I mean by planning? You have generative modeling tasks where you have to generate highly dependent tokens. Let's say, I hope you are all aware of the three sat problem, right? You have a bunch of literals which are satisfiability, ors and ands, right? And you want to satisfy all of them, right? You want this to be true. And can you find an assignment of binary variables such that this is true, right? So it's a very hard problem, and can neural networks solve it, right? It's a planning problem, and it is in some sense the prototypical planning problem, because most other planning problems can be reduced to a three sat, right? And it could be or molecule generation, right? So where structure actually matters, what is the relative position of each of those? Does it make sense together? Those are the kind of questions you ask in molecule generation. And we hope that diffusion models can maintain global constraints because it's generating everything together. It's not generating one at a time haphazardly without thinking what is going to happen later, right? Right. So this is one set of applications for diffusion models in this space, and the other one is speed. Okay, so we can easily produce parallelly multiple tokens, and we can which can actually give us speed up over autoregressive models because autoregressive models are forced to produce one token at a time, right? So this is another dimension of diffusion models which a lot of people pursue, and there are many hot startups which actually want to replace LLMs with because diffusion models are much faster, and there are demonstrations including from Google Diffusion where it's a blazing fast diffusion model. It's about 5x faster at batch size 1. Okay. Okay, so in the first case, flipping tokens one by one to main yeah. So in the first case, we want diffusion models to be slow, right? You don't want to generate too many things at once because it can be inaccurate, right? So we want to flip tokens one by one and do multiple rounds of denoising. However, this can be detrimental to speed. Okay, so in the second thing, uh, it could be hard to model joint distribution on large product space, and it assumes independent flip. So it could be detrimental to planning. So these two things don't go well together. So planning and speed are kind of orthogonal pursuits when we are dealing with diffusion models. Okay, so now in this rest of this talk, we'll think about how to use diffusion models to do constraint generation, which falls in the planning category where we want to be slow and we want to be accurate because things depend on each other. Okay, so in our research work, we introduced something called Interleaved Gibbs Diffusion, and it's a framework for generating discrete continuous data. It does not assume factorizability of reverse process, and it can capture strong dependencies needed for constraint generation. What does it mean? Usually in diffusion models, you flip multiple tokens at a time, multiple coordinates at a time, and when you do that, you assume that it's coming from a product distribution. However, when you have constraints, they're not really independent. You can't assume that they're independent, and that can lead to errors where constraints are violated. So we don't assume factorizability, and we flip these tokens one by one. Okay, and this supports conditional generation, and it has inference time strategy for scaling, improving generations, and this gives you state of the art performance on layout generation, molecule generation, and random 3-set programs. Okay. Okay, so this is a discrete continuous model. So there are discrete variables and continuous variables. Okay, so we bunch them together like this. So first variable is 1.2, which is continuous. Second one is E, and then the third one is 0.2, 0.1. So it's a tuple of data. It's a vector of 2D embedded in the middle, and then there's an A, and that's this is our data point. So let's see how the forward process corrupts this data. So yeah, yeah, yeah.
Are the discrete and continuous variable tokens fixed? Meaning, should the once it's a discrete token that always that position will always remain discrete in this model, or it can, for example, can the 1.2 be in the fourth position at some other point? Is that allowed? Or
Okay, so we'll fix an order, and then we'll say that forever in this modeling procedure, this will be fixed here.
okay.
First coordinate is for
Okay.
Continuous, second one is for discrete, and so on.
Okay. Thanks.
Okay, so let's look at the forward process in this case. So we kind of add Gaussian noise, so it moves slightly far away from 1.2. Rest of them are unaffected, and then we flip to independent with probability 0.5. It flipped to A, right? And then we add slight amount of Gaussian noise. It moved slightly far away from 0.2 to 0.1, and similarly we keep on adding noise and until the end where we end up with no information about where we started out with. It's completely gone, and it's a product distribution. The continuous variables look like a standard Gaussian, and then the discrete variables look like uniformly sampled from some distribution, from the base distribution, right? So this is the forward process, and we use the round robin order. We go on multiple rounds to keep on noising them. Okay, so this is a time-independent round-robin Gibbs type Markov chain. Right? It converges to stationarity after O of log n passes. As I said, we are not concerned about speed. We want accuracy, with something which cannot be obtained by autoregressive models. Okay, and it noises each coordinate one by one. Okay, so the reverse process is like, okay, we have such a noisy vector at some intermediate stage, and then what we do is we sample partially noised to position 2 given rest of them, right? So we go and ask the question, what should be, okay, I see a z here now, okay, but then given the rest of the context, is z the right one? What is the posterior probability distribution which goes in this place? And that maybe turns out to be a. Okay, we sample a here, maybe that's more likely to be there than z. Similarly, in the when we encounter a continuous random variable, we do a continuous um, denoising step where we sample partially noise position 1 given the rest of the context, that is a 0.32 minus 0.1 af, right? And let's say the algorithm determines that, okay, this should actually be 1.01, and so on, and then eventually we keep on flipping them until we end up with lower noise, and finally the final output sample, which actually mimics the dataset distribution. uh, so here the reverse order is the order in which we are denoising should be in the reverse as the forward process, and this is a time dependent Markov chain like in diffusion models, which also have time dependent Markov processes in the reverse process. Forward process is time independent, or reverse process is time dependent. Okay, and continuous denoiser can be implemented via standard diffusion model framework. So basically, what we do in continuous denoise is that we run a continuous diffusion model for, let's say, 200 steps, for example, right? And then we say, okay, it has partially denoised. Okay, so that's obvious. So we know how to design the continuous denoiser. We give it context as the rest of the thing, and then we kind of ask it to denoise it from noise level A to noise level B, and it does that. The question is how to design the discrete sampler. Here we have uh, a pseudocode for understanding the reverse process. So at each step, we can either call the discrete denoiser, or we call the continuous denoiser and keep on moving each coordinate to a less and less denoised state. Okay, right. Uh, So what we show is that if the denoisers are ideal, that is, if continuous denoise what step ideally samples from the correct conditional distribution, and and the discrete denoiser also samples from the correct conditional distribution, then we recover the target distribution pi exactly. Such a guarantee does not exist if we assume factorizability, right? And that's why we do not assume factorizability here. And essentially, what we are doing here is we are sacrificing speed for an exact reversal. Okay, so we learn the denoisers using a procedure called Glauber generative model. So basically, what we do is, okay, this is a very bespoke algorithm, which I won't describe in detail, but we reduce denoising diffusion to binary classification. Okay, so suppose I see a string of tokens, and then I see a position it at time t, and then I ask the question, okay, given that I see this here, what is the probability that it came from noise versus what is the probability that it came from signal, right? It's a binary classification task. Okay, and then we try to solve this binary classification task, and once you know this conditional distribution of whether it is true or false, whether it is signal or noise, then you can apply Bayes rule and actually produce the denoising distribution. And of course, continuous diffusion can be learned by, of course, score matching, which you've studied the whole semester. Okay, so here is the training algorithm, which I'll give you a high level idea of. So basically, if we sample some random time t and go to time it, coordinate it, and we either learn the discrete denoiser if the noising step was discrete, or we learn the continuous denoiser if the coordinate in question is continuous. And And binary mask here indicates that which elements are fixed during forward and reverse process and they're handled appropriately. This is useful for conditional generation. Suppose you want to condition on certain parameters in the state space and then only denoise the rest. This kind of actually helps you with the right conditional distribution. I guess you would have seen these things in the lecture on inverse problems and so on. Okay, so let me give you a first example. This is 3SAT. So here we pick n variables and we draw about 100k random 3SAT instances at the hardness threshold. Right, there is a number of clauses. If you have those number of clauses, you start the 3SAT problem starts becoming very hard. And we know that this is an NP complete problem, and there is no known algorithm which can solve it polynomial time, and it is conjectured that there is no algorithm which can solve it in polynomial time. Right, in practice people use something called the branch and bound algorithm to solve these kind of 3SAT problems, right? And it can solve up to, let's say, 10 to the 4, 10 to the 5 in industrial solvers. We are only interested in n equals 9, and I want to tell you that, okay, we are not told the model that it's seeing 3SAT data. It just sees a problem statement and a satisfying variable assignment. So these are the clauses which is given in green here, and then these little boxes here are the assignments for the variables x1 to x9. Right, so we just show them this correct assignment and clauses, and we don't even tell it that it's solving 3SAT, right? And then we show these 100k samples and then train the IGD sampler to sample a satisfying variable given an unseen clause. Okay, so can it learn to satisfy the constraint? Here are a couple of denoising runs where it has actually learned how to solve 3SAT assignments. So, okay, so if you see the animation here, red means that the clauses are not satisfied. Slowly, it keeps on assigning the right variable values until all the clauses are satisfied. Right, and it generalizes to unseen 3SAT instances, so which we thought was, which was great because um, we haven't even told it what it's doing. It just figured out what to do from raw data. Okay, so these are the results for 3SAT. The first bar graph here is GPT-2 from scratch. We train a GPT-2 model, very small model, 6 million model, and it performs okay at n equals 5, but its performance drops drastically by when you increase n because it is trying to produce tokens one by one. However, mass diffusion models and IGD, which is our model, perform very well. Our model, which actually does not assume factorizability, is much better than mass diffusion model, especially for larger n. Okay, so we also did experiments on layout generation. The generation runs look something like this. Initially, it starts with overlapping uh, kind of boxes everywhere, random types of boxes. Eventually, it starts moving things around and slowly figures out where everything belongs and gives a nice looking layout. Even in this, people measure things like FID, which should be small, and MIOU, that is intersection over union, right? And in both of these, we were able to beat methods with lower FID and higher MOU than baseline algorithms. I want to note that DLT, layout diffusion, and layout flow, they all use domain specific architectures and domain specific loss functions, which we do not use. We just use a standard diffusion transformer, right? And we are able to get these results, and all because we keep it principled. Okay, and this is ours. Okay, so and then another data set we tried out was molecule generation. We show it something called QM9 data set, and it has about 100,000 molecules. Well, that is okay. So it will have up to 30 atoms, and the positions, Cartesian positions of each atom, and the type of atom it is, let's say oxygen, carbon, nitrogen, or hydrogen. And we want to figure out a discrete assignment, that is a molecule type, and the spatial positions of these molecules such that the generated molecules has atom stability, that is there are no weird bond angles, and valencies are satisfied, molecule stability where the whole molecule is stable, every atom is stable, and validity, that is there are many other criteria and toolkits which actually tell you whether a molecule is valid or not. And uniqueness, that is, okay, you don't want to keep generating the same thing again and again. So in all of these parameters we score highly, we are able to improve state of the art in terms of stability and validity. Okay, so you might not be able to see the difference in the thing, but let me assure you, in my paper we show that actually it's a few percentage higher in terms of stability and validity. Okay, yeah, so with this I'll stop my talk, and I'm happy to answer any questions you might have.
You said you wanted to ask something.
Yeah, I do have a question. So, first of all, thank you very much for the talk. It was great. And so, one question I have is like, how do you like both in the base GGM, which is like the prior art of this of the work you described, and this more like multimodal. So, I guess maybe the
Mhm.
question for multimodal, like, how do you select which tokens to unmask in, or like which tokens to yeah, like what is the base rule for discrete, I guess, for like remasking or re-going back to the input sequence from the output.
All right, so basically this is a multinomial diffusion in some sense, in the sense
Yeah.
that there's no mask.
Yeah, there's no
uh,
mask. Yeah.
right, so you okay, for each thing, okay, what we are predicting is its posterior distribution.
Right.
Okay, given that this is a noisy sequence, what is the law of this particular thing, and we sample from that.
Yep.
And that's what we do, and we go in a round robin order. It's fixed, just because we don't want to have biases in figuring out where to go and device. Because in the forward process it's uniform, but in the backward process we don't know what is the right distribution of where we should go and intervene, right? What is the right
Oh, I
distribution of the
see.
indices.
So you just sample from the post. So you like round robin select the token. You sample from the
Mm,
posterior, and you
correct.
just go with that. Like
Yeah.
you have committed to it basically.
Yes, correct.
Got it. Okay. All right. Thanks.
Well, these papers are available, I guess, on archive, or is it internal, or?
Oh, it's available on archive. Yeah, if it's internal I won't be allowed to actually even talk about this. It's all available. Yeah.
So maybe you can put a link here. As you said, we'll upload these slides, but in the slides itself, you can put maybe just archive links in the last slide before we upload it. That way, people who have access to the Dropbox can have access to this as well.
Sure, sounds good. I'll give you access with after adding those things. Okay.
Anybody, anything else? Okay. Thanks very much, Dheeraj. Really appreciate.
Thanks a lot, Sanjay, for hosting me. Yeah.
Thank you so much. So,
See you.
going to, I guess, with this, it sort of brings the recording of this semester to the end. Thank you all, and your projects are due in a week or 2 weeks, and so see you then. Thanks.